Okay, so we've talked about trees, and we talked about tree traversal, and we certainly could do like a searching type thing. Did we leave this off in any place that made sense? Or I think we finished writing the in order traversal, right? And it just displayed the stuff, and we have it in JSON format or. So what kinds of applications could we use trees for? When would you use a tree? We've talked about databases, right? Things like that where we need to search stuff, and they're, we want to almost have like a path of least resistance as we kind of walk through the tree. And we've also talked about at the high level the idea of self-balancing trees or rebalancing a tree to kind of give you the best average search time across the tree. Where rebalancing algorithms are a little bit sketch, I guess, in that they're very expensive, they're not easy to implement, and then it kind of becomes this toss-up as to whether or not it's which is going to cost you more time. Sometimes having a slower search or having to constantly rebalance your tree. So then it becomes this argument: if you're adding stuff to your tree very often, rebalancing maybe doesn't make a whole lot of sense. The easiest way to rebalance is after each add. If you go through and have to do like kind of a recursive rebalance where you wait till your tree gets like significantly out of whack before you rebalance, it's a lot more difficult to rebalance a tree that's extremely lopsided. It's much easier, yet still somewhat difficult, to rebalance a tree as soon as it gets out of balance. You know where it's out of balance. You know the place that the node that was just added that threw it out of balance, so you can start your focus there, as opposed to having to kind of walk through the tree and figure out the places where it's broken, and then it's almost like turning a dial to rebalance a tree. So if the tree is deep on the right side, when you turn it, you're lifting that right side up and dropping the left side down, and you're giving it a brand new root node, is effectively what you're doing. But that's a very expensive endeavor. And like I said, the best time to rebalance a tree is right after an add that throws it out of balance. Okay, well, so with that in mind, if it's expensive and you have an application where you're doing lots and lots and lots of ads and very few searches, is it worthwhile to rebalance? We don't care how balanced your tree is if you're rarely searching it, right? Same thing is if we say that searching a tree that is out of balance can be slower than searching a tree that is in balance on average. How much slower from a human perception is kind of the idea. And as computers get faster and faster and faster, we maybe care less and less for certain applications. Where things really go sideways with this in mind is when you have multiple user applications. So now you're looking at these high-end databases like an Oracle or a Microsoft SQL Server that isn't just responding to a single person at a dentist's office searching up a patient record, right? Where it doesn't matter if your tree is horrifically out of balance. You have 500 patients. It's one person doing a search at a time. You're not going to notice. It's going to be fast. It's going to feel instantaneously, as opposed to you have people doing a Google search, or you have folks on Amazon searching for a certain product. There's a lot more than one person doing a search at the same time on the same data, right? Somewhere Amazon has a gigantic product list. I don't know how many total items are in Amazon's database, but it's a lot, right? And they probably have that product list duplicated some number of times to kind of load balance searches. So if I'm searching for something and you're searching for something at the same time, it's possible we're looking through two separate catalogs, even though those catalogs are kept in sync, just for performance reasons. But we can make the assumption that it's more than just you and I who are searching for stuff at the same time on Amazon. So if we just kind of take that down and we assume there's one database at Amazon, even though there's probably several, we assume there's one database that has their content collection. You have 10,000 people at any one point in time searching that. And I mean, I don't have real numbers, but I assume that's not a ridiculous number. That feels like it's a number that's in the ballpark of reasonable. So 10,000 searches at any given moment on that one database. Now search time per search becomes a thing, right? One of those searches on an unbalanced tree might not be that big of a deal, but 10,000 within 1 second, you might feel it, right? And that might be something that you need to remedy. Having said that, how often do you think Amazon adds new products into its listing? Okay, fair enough. Which happens more often? Searching products or adding new products? Easily, right? Searching products happens more often. So in that particular case, we would definitely prefer searching to be fast, even if adding a new product is a little bit slower, especially when you consider that adding a product isn't necessarily customer facing, right? If I'm Amazon and I want my customers to have a great user experience, and I want to get a new product in there, even if it took 20 minutes to add the new product. I mean, I'm sure it doesn't take that long, but even if it did, that's not the end of the world. Customers aren't going to see it. You'll start the batch job to add the new thing, and you go to lunch. And you come back, and the new product has been added, and the tree's been rebalanced, and everybody's happy. Although now you have concurrency type of things to consider. So maybe they add the product, maybe they have kind of a master collection for their catalog. So they add it there, and then that gets synced across the other ones. Well, now you got to think about syncing it without hurting that search performance of. So what you probably do is you probably take a couple of your databases offline, you sync to those, then you take other ones, you bring those online and take other ones offline and that kind of stuff. So at any point in time, you might reduce the number of available catalogs to your end users that they're sharing to kind of load balance the performance. But you're not artificially slowing it down while you're doing this like weird sync across the board. Outside of that, you could also be very strategic. If you added one item to a tree, and you know that only this portion of the tree was affected, you could be targeted, and instead of syncing the entire tree, you can go and sync that one part. Little things like that kind of balance out. Okay, so we can say that's the purpose of rebalancing a tree. Let's look at least at the high level here. Let's just steal this tree. Whatever. Remind me, what was coupling again? Should have been something I think I referenced that you should have probably talked about in software engineering at some point. Go ahead.
Coupling is really just one part of your code depends on the other.
Okay, good or bad?
Well, it's best to have as little of it as possible. But
Okay.
You're gonna have to have some of it.
Yeah, so unavoidable sometimes, but probably a decent effort should be made to minimize it. Don't attach two things to each other that don't have to be attached, unless you're doing the lazy singleton thing. Then you just know you're going down a dark path, but it's okay. Sometimes I think programming does come down to that sometimes. Sometimes you make a decision just because it saves you time right now, and you think ahead and you're like, well, I'm probably not going to spend more time on this little thing here, so it's not going to really hurt anybody. Let's just do it. Let's say 6 out of 10 times is probably an okay move. But you're rolling the dice. right? But it also could be job security. If you've written code that's just so dependent on other things, and you have this little manifesto map that you've created, nobody else can read your code. You just have these lines drawn like, yeah, I actually have this variable stored as a static variable in a completely unrelated class. But whenever I need it, I use it from there. Nobody else can read that code, and you won't lose your job. So think about that next time you care more about employment than being a good programmer. So it's sort of recorded. All right, so let's look at some rebalancing stuff, and I'm going to take off this extraneous stuff for the moment. Okay, so when we say a tree is out of balance when one side of the tree is more than one level deeper than the other side of the tree. Okay, if it's within one, that we're going to say that's okay, because when you rebalance it, you might make it unbalanced the other direction. Okay, but if you get two or more levels deep, so the depth of this right-hand side is, you can say it's either 2 or you can say it's 3, depending on whether you count this as level 0 or level 1. So let's say this is depth 2, which is what we've been doing for our lexical address. This guy is depth 4. Correct? Okay. So how would you change this tree so that both sides are either the same depth or within one of each other? I mentioned thinking about this thing as kind of like it's a dial. All right, so you would pick a point that you're going to pivot about. Okay, so you're going to pick a pivot point where the dial is. So one of these subtrees becomes your dial, and there are different approaches to this. So different self-balancing algorithms approach the problem differently. And I'm telling you, they're all kind of complex. So let's look at it generically first. Okay? So what if I picked the 6 as my pivot point? So I'll just pick the top of the tree. I know I'm out of balance to the left. Okay? So I'm going to decide that the 6 is my pivot point. So I'm going to turn. Because I'm out of balance to the left, I'm going to turn to the right on that pivot point, which then will drag my tree around circularly. So what ends up happening is maybe this 5 becomes a new root node. And this stuff here kind of gets drugged down this way, right? All right, so I'm going to kind of move that off to the side here for a second. So 5 is my new root node. All right, now I have this secondary tree. So I've disconnected the left node from 6, or left subtree from 6, which was 5, because he's the new root node. So I've now pointed to him as the new root node. And I have this extra tree laying around over here, right? I've kind of depicted it as I've turned it to the right, but we've kind of lost the 6 for a minute, because that 6 was not a child of the 5. So what I did is I detached because we're rotating to the right, I've detached the left child of 6 from it. So this is now pointing to null. And then I made the head, the root node of our tree, point to the 5, which now leaves the subtree over here just sitting there. Okay, this was our short side. All right, now what can I do with this 6? Okay, so this is my current tree. Root node is 5. Everything to the let's actually think about this. Was this a broken tree to begin with? I'm trying to remember if this was. Oh, it's just laid out funny. So this 5 here is the right child of this 4, but it's left of this 5, even though it visually doesn't look like that. So let's spread this out a little bit. So our tree's not inaccurate. It's just visually a little bit misleading. Okay, I think that's less misleading now. So this 5 here is to the left of this 5. So it goes 5, 4, and then this 5 is to the right of this 4, which is to the left of this 5. Because everything to the left of the root node should be less than or equal to it. All right, so the tree was accurate, we just had it scrunched. All right, so we just spread it out a little bit here. So this stuff is all still the same. Okay, so now, let's say I place this 6. Where would this 6 go in this tree? Well, if I dropped a 6 here, remember we got the Plinko approach, right? That's the game, right? Plinko? You seem to be an expert on this. Yeah. All right, so we dropped the 6 in here. 6 is not less than or equal to 5, so it's greater than, so we'll try to add it to the right that exists, correct? All right, so the 6 would go here. What happens to these two 7s? Would they still be relative to that 6 in the same place? What kind of animal is this? Cat, dog, or tree? It's a tree. Okay, what kind of animal is this? Cat, dog, or tree? Okay, what kind of animal is this? It's a tree. Tree, tree, all these things are trees. When we add something to a tree, what are we adding? We're adding we could either add a payload or we could add a tree. So if I add this 6 to the 5, I'm saying I'm adding this tree to this tree. Now this tree still has crap hanging off of it. We didn't take the chainsaw and cut everything else off. We just cut this part off, right? So we still have like a little mini tree. It's like more like a shrub, all right? So we have a little mini tree here. So I'm going to take this entire tree and I'm going to add it here to the 5. Now, the reality is that this part of the tree over here is really kind of meaningless, right? I mean, it's already structurally where it needs to be, right? Because we added it at some previous point in time. That tree kind of grew up and stuff like that. Then we, got in there with a chainsaw, right apart, and then now we're going to add this guy back in, and it's probably going to take some chicken wire. Or do trees grow back together like that? I don't think so.
You can graft branches on the trees.
Really?
Yeah, that's how they do some of their mixing of different types of apples.
You seem to know a lot. You're like an arborist. That's a thing, right? Arborists?
No, I just studied it because I was studying John 15, where it talks about, or in Romans. No, it's in Romans where it talks about being able to graft the branch back onto a tree.
Oh, that's interesting. Oh.
And so we were studying about that.
Christian worldview. I'm taking credit for that. I coaxed it out of her. That's actually fascinating. So you were studying the Bible and decided to study how grafting branches onto trees works.
Because it talks about it.
Yeah, no, it's fascinating to me. Way more fascinating than you knowing about Plinko. All right. So, then this matches reality. We're good. All right, so we're going to drop this tree onto the top of this tree. The 6 is greater than 5, so we'll try to add it to the right. It fits to the right, correct? So since it fits to the right, we will go ahead and put it there. So we added this tree as this guy's right node. Now we ask the question, is this tree out of balance? It's not. This side has a depth of 0, 1, 2, 3. This guy has a depth of 0, 1, 2, 3, even though they look a little more spread out than that. That's really what it looks like. But even if it was 3 and 2, we're still fine. Okay? But these guys actually happen to be, we have a level tree at this point. It's legit. Right? So we've done our job. So far, so good. Okay? Because we need to ask the question, is a tree out of balance? How would we ask that question? So let's go back. Okay, and then I'm going to go ahead and, because I want to have these as my starting point here. There. Let's see, we always guaranteed that. Two. Okay, so that's going to be within 1.
Fives are supposed to be coming off before.
It's this. Like that. Look, and then maybe scoochy that guy over a little bit. Good enough. Okay, so we're out of balance. Good. Okay, so this side, this is 0, this is 1, this is 2, this is 0, this is 1, this is 2, this is 3, this is 4. All right, so how do we determine if a tree is out of balance? Algorithmically. So let's say that we were to write a function that was going to, because we can currently add a bunch of stuff to our tree, right? Let's say we're going to write a function that returns true or false. Tree is out of balance. How would we do that? Because we can look at this tree and we just did the counting, right? How do we determine that a tree is out of balance? What does it mean for a tree to be out of balance first? We have to understand the problem. What must be true for us to say a tree is out of balance?
One side of the tree is more levels than the other. Yeah.
More than one more level.
Yes.
Yeah, so it's the depth of one side, regardless of which side, is more than one level deeper than the depth of the other side. Okay, so will we agree that knowing the depth of a tree is an important thing? Now, we've implemented our tree as a tree of trees, correct? So is it a reasonable thing for me to ask the depth of any tree? Like if I ask, what's the depth of this tree? The tree that is the 6. The root node's the 6. What should the answer be? Is it the... Go ahead.
It should be 0 because it's nothing else.
Okay, I do see where you're going with that. We're not interested in where this guy's depth is. We're interested in, if this is the root node of a tree, what is the depth of the tree of which he's the root node? You said 4, right? Okay. Oh, is that not what you said?
No.
All right, say it again. Say 4.
4.
It's 4. Okay. All right, because we counted 2 different depths, right? When we went down the left-hand side, we came up with a 4. When we went down the right-hand side, we came up with a 2, correct? So the depth of a tree is the greater of its left and right depth, plus 1, plus itself. So if itself is a depth, but we can decide whether we count ourselves as 1 or we count ourselves as 0. We've been operating off of a depth 0. So this tree, if we just had 6 just sitting out here, this was our only tree, and we asked what's the depth of that tree, the depth of that tree would be 0, because he has nothing coming off of it, as opposed to he's not coming off of anything else. All right, so algorithmically, what did we do? The depth of a tree is the maximum of the depth of its left tree and the depth of its right tree, right subtree. So we'll ask, what is the depth of this tree? So this is 1, 2. We have to add 1 to it to get us down one more depth. So this is 1, 2, 3, 4. That's the depth of that tree. Now, keep in mind, we just did that as a human. All right, we're going to have to go back and really investigate what actually just happened there. Okay, but we came up with a 4. What's the depth of the right tree? We have 1, 2. Which is greater, 4 or 2? 4. That's the depth of this tree, the greater of those two. All right, now, just because we'll have more passes at this, how did we figure out that this was a 4? This guy says, I need to know the greater of my left tree depth and my right tree depth. So in order to do that, he's going to have to get his left tree depth and his right tree depth. And then later on, once he has those two numbers, he can decide which is bigger. Right? That's what we just did. We said which is bigger, 4 or 2. All right, so let's just focus on getting our left tree depth right now. So our left tree depth will be 1 plus, assuming we have a left child, will be 1 plus the depth of this tree. Okay, what's the depth of this tree? So I'm going to put the 1 plus here. What's the depth of this tree?
1 plus the depth of his left tree, because he doesn't have a right tree.
Okay, right. So it's again. This is that whole like recursion type thing. What do I call it? Relative? What did I name it? Pseudo recursion. That's a perfect name for it. I'm glad I invented it. Okay, so pseudo recursion. So the depth of this tree is the maximum of the depth of his left tree and the depth of his right tree. As she pointed out, this guy has no right tree, so we don't need to go down that path. So the depth of his left tree is 1 plus the depth of this tree. What's the depth of that tree? It's the maximum of the depth of his left tree and the depth of his right tree. Okay, so we're going to have a 1 plus here, and we're going to have a 1 plus here. What's the depth of this tree? Zero. Right, we bottomed out. So we're done over here. So this guy's finally a 0. So we hit the end point there. What's the depth of this tree? It's the maximum of his left tree or his right tree. He doesn't have a right tree, so this guy's going to be 1 plus the depth of his left tree, which is a 0. So we have 1 plus 1 plus 0, so this is a 2. We have 1 plus 0, which is a 1. So the depth of this tree is the maximum of 1 and a 2, which is a 2. Plus 1 is a 3. Plus 1 is a 4. That's the depth of the left tree. Depth of the right tree is 1 plus the depth of this tree. What's the depth of this tree? It's the maximum of the depth of his left tree and the depth of his right tree. So depth of his left tree is 1 plus the depth of this guy, which is 0. Depth of his right tree is illegal. So the depth of the left tree is 1 versus illegal. Answer is 1. 1 plus 1 is 2. Depth of this guy's right tree is 2. So we come up with 2 different answers here. We get a 2 on this side, and we get a 4 on this side. And then we pick the maximum of those. Make sense? That's the depth of a tree given its root node. So we kept performing the same action over and over and over and over again, right? Okay, so let's write that. So we'll go into our binary tree. Now, our binary tree has a payload, and it's a tree of binary trees, right? So we should be able to ask any binary tree, what is your depth? Make sense? The depth is always going to return an integer. It's going to be the maximum of, potentially, a maximum of two values. Okay? So int, call this guy get depth. Okay? So, this guy needs to figure out his depth. And he's going to return an answer. And the answer is going to be a maximum of two values. So we need to get left depth and we need to get right depth. Okay? So let's think about left depth and right depth. We're going to say int left depth. Maybe we start this guy off at -1. Just for right now. Right depth is -1. With the idea of us being able to notice a -1 as being an illegal depth. So if I'm saying take the maximum of something real and a -1, the something real wins. Now, if I took something real, I took the actual maximum -1 and didn't even treat it as a illegal position, wouldn't this guy always win anyways? So I've actually removed a conditional. I don't have to say, if this guy's -1, just pick this guy as the winner. If this guy's -1, just pick this guy as the winner. Instead, I could just say, maximum of these two. I'm done. Okay? So I'll start them both at -1 and then potentially change them if they should be changed. So when should left depth change? Under what circumstance should left depth change? Go ahead.
When there is a left tree,
When there's a left tree. How do I determine if there's a left tree?
if its value is not null.
Okay. So if this dot left tree not equal to null, that means I actually have a real left tree that should have the capability of reporting to me his depth. Okay? So that means left depth is not going to remain a -1. It's going to be something else. So what will left depth become? I need to say left depth nailed it. Left depth equals what? We're going to change the -1. What should it actually equal? What?
Depth plus the get depth of the left tree.
Okay, so if we go back to our little chart here, we've been doing a whole lot of 1 pluses, right? So we don't want to take the current left depth because we set that at -1. Yep, so this guy's going to be 1 plus this dot left tree dot get depth. So it's 1 plus the depth of the left tree. Make sense? And this is our pseudo recursive call, correct? It's just such a beautiful way of describing that. Pseudo recursion. So I'm currently in my get depth function of this tree. Now I want to call the get depth function of the left tree, which is a different tree but the same function for that tree. Similarly, if this dot right tree is not equal to null, then we'll say right depth is equal to 1 plus this dot right tree dot get depth. Okay. So now, and that's going to keep going down the line, right? Now I have a value in left depth and I have a value in right depth. Okay, so somebody else is going to help me solve this problem. This next part is an easy question. Okay, I have two variables. I have left depth and I have right depth. I want to know which of those is greater. Okay, how do I determine which is the greater value between left depth and right depth and ultimately return that greater value? We're doing that thing where it's like, which is bigger, 4 or 2? Go ahead.
We just do like if right depth is greater than left depth, then you can print out the right depth else.
Okay, but instead of printing out, what do I want to do?
Treat them. That's specific. Oh,
I'm not printing it. What am I doing with it? Returning it. All right, so I want to return right depth. Otherwise, we'll return left depth. Now, we're okay returning the left depth here, right? If right depth isn't greater, then we know that left depth is either the same or it's greater. If it's the same, it didn't matter which of the two numbers we returned. We returned 4, we returned 4. The 4 is 4. So we're okay. All right, so calculate the depth, then return the maximum of my left and right depth. So that's what get depth will always return. All right. Now, this currently has a bug in it. What's our bug? When we came in here, we had a lot of scenarios where we had 0 and 0 and 0. Remember those guys? Where this guy reported his depth as being 0. This guy reported his depth as being 0, so on and so forth. As we have it right now, this -1 will artificially shrink each tree, eventually, by 1 depth. Because we're going to return a -1. So we're going to add 1 plus a -1, which is going to give us a net 0, 1 level up. So we're saying, look, in a worst case scenario, a tree's depth will be 0. If it exists at all, it's at least a 0. Same thing with this guy. If he exists at all, it's at least a 0. Make sense? Now we can go ahead and do the same stuff we did before. It's either going to remain a 0, and if they both remain a 0, if we're at the bottom, okay, in this particular case, the depth of the left and right tree of this guy is 0. They aren't a thing, right? So what's the maximum of left and right? Maximum of 0 or 0? Got a big old winner of 0. So that's what he's going to return is a 0, which is what he should have returned. Okay, he's effectively, that ends that pseudo recursion. This is the end of the line. I can't call any more functions. We've hit rock bottom. I have no people. This is pyramid scheme stuff. Actually, somebody told me over the weekend, I think, that I think it's somewhere in the acceptable use policy at Concordia that you're not allowed to use campus technology for working in pyramid schemes, like the get-rich-quick stuff. Like that. Have you ever actually read the little book? Nobody reads those. That's like, I didn't read it either, but I mean, apparently that's a thing. I bet you there's probably something in there about BitTorrent as well. I gotta tell you what, I took a screenshot of my office. I was getting like 800 megabits per second or something in my office yesterday. Pretty legit speeds. Unfortunately, I wasn't doing it with BitTorrent in that particular case. Part of family, cat, and dog. See, that always seems dangerous to me. Like, shouldn't notifications from Facebook like not pop up when you're like on a projector? Like, that should be something that's like disabled, right? Or can I disable that? No. Oh, I see. It's actually not a Facebook thing. It's a... So I should remove that. That's just going to be golf videos, but yeah, I remove that. I'm significantly less concerned about, one of my golf video subscriptions popping up than, of course, I have all perfectly good Christian friends on Facebook, but every now and then somebody might be known to say something or post something that I probably don't want to have recorded in front of an audience. Although I would find it funny. I think I shared with you, it was in a grad class one time. We were generating strings. And did I tell this story? We were generating strings that were between 3 and 8 characters long, just randomizing strings for a sorting algorithm that was sorting strings alphabetically. So within that random thing, and it was upper and lowercase letters, so you had 52 different possible combinations for each individual character. We happened to generate a 4-letter word completely at random on recording, and it even started with the capital F. It was solid. Moon's aligned. I mean, I think it's biblical or something, isn't it? Maybe not. It might not be. But yeah, it was pretty funny. We all got a pretty decent laugh out of that. Who would have thought? Just the chance. I guess at any level, all words are just made up, right? But yeah, I mean, it was. The rest of it was all lowercase. It was like really grammatically correct. And it really stood out too because all the rest of them just looked like random gibberish. It was right there in the middle of the screen. Oh, it was great. All right, so let's go ahead and test this guy. We need to, I think last class, that was the order we visited it in. All right, so we need to create this tree in the right order. So we're going to add a 6 first, then we can add a 5 or a 7. Either one of those will dump into those places. We can add another 7, that'll get us so now the right tree is completely done. Then we can add a 4, then a 3, then a 5, then a 5. I think that'll generate that tree. All right, so we're going to add those nodes in that order, ask its depth, and it should give us a 4, the maximum of the 4 and the 2. All right, that'll be our exhaustive test for all trees that may ever exist. We're going to do that one tree. All right, so let's give ourselves that was our visit in order, so let's give ourselves a get depth. And visit in order. What did visit? Oh, visit in order just printed something, right? Okay, we'll just do the same thing with get depth. That way we don't have to modify our interface to give us a new landing zone. All right, so we'll go into main activity here. We'll do public void get depth button pressed. Take a view v as a parameter. All right, and we're going to go ahead and we're going to say system.out.println, and we're going to say the word depth concatenated with this dot bt dot get depth. All right, so that's what that guy is going to do. I'm actually going to run this real quick for no good reason other than I have somehow convinced myself that this increases the likelihood of our on-click working. I think there was no software update this time. Sign of the apocalypse. That's biblical, right? Point. Okay. So now I can go hook that. Let's stop that. Let's go in here. Let's put this guy's on click. Get depth. Run this again. Have that checkbox of use this next time you want to launch this if it doesn't do that. If it doesn't just trust me that I don't want to have to answer that question again. It's just disheartening is what it is. All right, so I need to 6577. Well, I guess I could have used that same 7 twice. 4355. 4, 3, 5, 5. Okay. Get depth. Well, it didn't crash. What's it? Android monitor, this guy. There's our depth of 4. All right, so clearly it'll work perfectly for all trees that ever exist. All right, so now, that doesn't sound reasonable to you? I'm sure it will. I've yet to introduce a bug into my code unless it was on purpose. So now we can ask a tree what its depth is. How do we then follow that up now that we have that ability? We've run to Home Depot, we've gotten the necessary materials, we've built the ability to ask a tree what its depth is. Now I want to be able to ask the question, are you out of balance? How do I do that? What does it mean again? You reminded us before. What does it mean for a tree to be out of balance?
So the levels are offset.
By?
1. Or, yeah.
More than
More than
one.
Yeah.
More than one off.
That's what I thought.
Yeah, within one is fine. That's wiggle room, right? So more than one off is it's out of balance. Okay, so we want to just want to answer the question next of, are you out of balance? We're not going to do anything about it. It's like that commercial where it's like the dentist and he's just a cavity monitor. Have you seen those? Like this guy goes in there. There's another one. It's the security guard where he lets you know whether there's a problem, but he doesn't actually do anything about it. Yeah, the dentist one. It's like he looks like a dentist and he's in this guy's mouth and he's like, oh man, that's like the worst cavity I've ever seen in my life. And then the guy says, okay, you ready to break for lunch? And the guy's like, aren't you going to fix it? It's like, oh, I'm just a dental monitor. I'm not a dentist. It's like, the guy's still, yeah. You haven't seen those? I'm the only one? You don't watch enough TV. Must be giving too much homework. All right. So you mentioned that a tree is out of balance if its left and right side have a depth that are greater than 1 away from each other. Correct? Okay. Now, do we have the ability to get the depth of my left and the depth of my right? Because my left tree is a tree. My right tree is a tree, if they exist, right? So I can ask each one of them, what's your depth? And then what's your depth? So I have 2 numbers. So now I have those 2 numbers. How do I actually use those 2 numbers to determine whether or not the tree is out of balance? So I got a 4 and I got a 2. Is that tree out of balance? Yeah. How did I do that? How did you figure that out as a human? So a human would just say, oh yeah, those numbers are more than 1 apart from each other. How do I ask the question in Java, is this number farther away from this number than 1?
This is the one number greater than the other number plus 1.
Ah, okay. So is this number greater than this number plus 1? Well, what if this guy was You know, what if we had 4 and 8?
And also, even then you have to.
You have to you have to do the flip side. Okay. Couldn't we also subtract them and take the absolute value? Yeah, so we can ask 2 questions if we want, which is fine. I mean, I'm not even necessarily arguing that one's faster than the other. You know, but I could take 4 minus 2, or I could take 2 minus 4 and take the absolute value of that. And if it's something that's larger than 1, we're out of balance. Right? Okay. So, well, I'm already in this application. So we're going to go into binary tree. We're going to write a function, public. Now, I want this function to be called is out of balance. All right. Now, this guy is going to probably return whether or not it's out of balance. What would a reasonable return type for this be? Boolean. Okay, good. Man, you said that with confidence. I like that. Yeah, you're much better with that than you are with just numbers. You know, it's even the simplest numbers, really. So.
Calculator for everything.
Well, you think you'd be getting decent because you said your daughter's 2?
10 and a half months.
10 and a half. Oh, yeah. So that's what I was getting at. So, you know, when kids are really little, you measure everything in months, right? That was like a joke from some movie where I think a kid was like 6 or something like that. Like 79 months. At what point is it no longer months? It's a year.
I've talked to my wife with this too. We've decided once she's a year, it's going to be she's a year and this many months. There's no like she's 24 months. We're not doing that.
Yeah, but so when does that end though? Like if somebody asks you how old you are now, you don't say you're this age in 7 months.
That's true. We haven't.
You don't treat every aspect of your life algorithmically, where it has to be an unambiguous approach to.
Not always. No. Nope.
Used to say she's a year and a half.
Yeah, it's not even going to be a year and 6 months. It's a year and a half.
That's true. I don't know.
I mean that. Now we're getting all over the place here. I mean, there's not even you have no consistency whatsoever in this.
That's true. So maybe at 2, she's just.
She's
age.
2.
Yeah, and 2 or 3. She's not anything in between. No months.
Okay.
At that point, we'll do halves.
I was gonna say.
And then at 4, we'll just say
Okay, we're gonna have to check back in on this. I'm gonna see him like years later. She's in her 30s. Yeah, she's 2,200 months. I don't know how many months are you when you're 30? Let's see let's see. So 39 times 12. I'm 468 months old. Well, no, actually, I'm older than that. How many months from January are we right now? 3?
3 to 4 depends on when it's in there.
Yeah.
End of January.
So 3.
Oh, we need to put decimal places on this. Apparently, 0.26 months. Well, leap years. How do we handle that? That's pretty funny. All right, so this guy's going to return a Boolean, whether or not it's out of balance. Okay, so we need to calculate the depth of the left and the right, correct? All right, so we're going to say int left depth is equal to 0, int right depth is equal to 0. Now, keep in mind that before, we were reporting what our depth was. Now what we're reporting is whether or not we are part of a tree that is out of balance. Does that make sense? That's what we're actually reporting. We don't really care what our depth is. What we care is if we look down the left-hand side, we look down the right-hand side, does one have a more than one greater depth than the other? Okay? So we have left and right. Now we're going to ask the question, if this dot left tree is not equal to null, if we have a left tree, then we'll say left depth is equal to this dot left tree dot get depth. we'll get the actual depth of our left tree. Then we'll say if this dot right tree is not equal to null, then we'll say right depth is equal to this dot right tree dot get depth. Now we have our two depths, okay? One way or another. If we didn't have a left or right tree, the depth of that was 0, and that's okay. All right, so now we want to ask the question, are we out of balance? Okay, so let's use my, my approach, since I'm not sure if you've seen how to take the absolute value of a number before. Okay, well, remind me. Not, I mean, I don't know. What does it mean? What's the absolute value of a number? What does that mean? Go ahead.
Well, like, I know it's like always positive, so it's like the absolute value of -1, it would just be 1. So it's always positive.
Okay, gotcha. So we need to take whatever the number is and make sure it's a positive version of itself. If it's already positive, we're good. If it's a negative version, make it positive. That means you multiply it by -1. Negative number times -1 gives you a positive. Okay? Or we can use a built-in function. Okay? So what we're going to do is we're going to say int difference is equal, nailed it, is equal to math.abs. And we're going to say left depth minus right depth. So there exists in Java a math class that has methods in it. So we're going to subtract right depth from left depth, giving us a value. We will then take the absolute value of that and store that in difference. And we want to ultimately return whether or not difference is, so we are out of balance if difference is greater than 1. Correct? So we'll return difference greater than 1. If it's not greater than 1, we're not out of balance. But if it is greater than 1, it's going to return true. We are out of balance. Does that make sense? So question. Well, here, we'll start with the remedial version of this. I'm just a little bit concerned about this crowd post-Easter. What kind of animal is this? Cat, dog, field, or method? It's a method. How do you know?
It's like, yeah, I'm just assuming because like it's an absolute value it's going to use for us. It's a built-in.
All right, so it's a method. You're just assuming.
Yeah.
All right, that's a bad answer. Let's come up with a better answer. How do you know it's a method? Go back to think 250. How do you know something's a method? Then think 200. How do you know something's a method? It's got a parameter list. You got open and close parentheses, those guys. That makes it a method, right? All right, so this guy is a method because we see this kind of crap here. He could also be a constructor potentially, but how do we know this guy's not a constructor?
Doesn't have the same name as
Potentially.
It's not making a new one.
That's the kicker, right? Whenever we see a constructor in the wild, it's always preceded by the new keyword. We don't see the new keyword here, so not a constructor. All right, so this guy's not a constructor because constructor is the only kind of only other kind of wild animal that have those parentheses in them, right? Okay, so not a constructor. See some parentheses. Must be a method. All right, what kind of method is this? Class method or instance method? And how do you know? Don't get this one wrong. You're not very talkative today, Van. Usually you're significantly more talkative today. Is the hair product kind of, is it seeping? Is it seeping in? Is it a thing?
No, not.
You're not even paying attention. You're working on homework for a different class, aren't you?
I'm not.
I called that so quickly. Is that what's happening? You're working on homework for a different class?
No.
Just playing games?
Nope.
So you got an answer for me? Or do you need me to re-ask the question? What do you got? You got something for me, Bakari? What kind of method is this? Class method or instance method? And how do you know? This guy right here. Should be automatic for us at this point. Maybe it'll help if you remind me, how do we call class methods versus how do we call instance methods? Oh, go ahead.
Well, class methods we have to use the name of the class.
Okay, we have to use the name of the class in which the method was defined. What about instance methods? We call it using an instance of the class in which it was defined. So class methods, we use the class name. Instance methods, we use the instance name, kind of like we were doing out here. So here, visit in order. We're calling it with a instance of the binary tree class. All right. So what we really need to determine here is what this dude is. The dude I'm calling ABS with, is he a instance of a class or is he a class name itself? Go ahead. Class name itself. How do you know?
One thing is a capital letter.
All right, well, which isn't a positive identification, but it lends us to believe. Class names typically start with capital letters.
But then we never instantiated it.
Okay, yeah, we didn't create our own variable. Saying as far as we know, there's nothing in scope that has a that came right before an equal sign and a new keyword. We never created an instance of that dude. Okay, so we don't have a variable called math, so we don't have an instance of the math class. This guy has capital letters, so he has I'm a class written all over him, right? So since this guy is a class and this guy is a method, he must be a class method because we're calling it using the name of a class in which this method must have been defined. Does that make sense? Very important that we can identify that stuff because if we go into the documentation and we go and look up the class java.lang.math, we'll see in there that we have a whole bunch of static methods. And when we have static in front of a method, that tells us it's a class method. That's how we identify a class method when we look at its implementation. That then tells us how we should call that method. So since the ABS method has the keyword static in front of it, I know that the way I call it is by using the name of the class in which ABS was implemented, followed by the method name. That make sense? All right, so important stuff. All right, so this is our out of balance method. For Thursday, and we're not even going to test this, I'm sure it works. For Thursday, fix it if it doesn't work. Then I want you to add an ability to this that tells us which side, in the event a tree is out of balance. Is it out of balance to the left or is it out of balance to the right? So give me some sort of feedback either in your interface or written out to the console, not just whether a tree is out of balance, but how it's out of balance. That make sense?
How is it like
Out of balance to the left or out of balance to the right?
not the number?
Yeah, not the specific depth, because that's going to dictate to us what our move's going to be, right? How we're going to react to it. So we're going to take the one little baby step forward. We now have a function that says, are you out of balance? Now I want you to follow it up by telling me, if it's out of balance, how? Is it out of balance? Is it too heavy to the left or is it too heavy to the right? That's it. Make sense? All right. I'll see everybody on Thursday.